I'm going to wait till we get to rate 120. All right, so hello everyone. We are going to start today's lesson. And as you can see, today's lesson is on something called binomial expansion and Pascal's triangle. So what is binomial expansion? Well, the word binomial means two terms. So I've got three examples here. A plus b to the power of 2, a plus b to the power of 3, dot, 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 a plus b to the power of 10. Is there a faster way of expanding those kinds of things without necessarily having to use the normal techniques that we usually use? And the answer is yes, and that's where Pascal's triangle is going to come into play. So if you've never heard of Pascal's triangle before, I will be showing you what that is on the next slide. But to get there, we have to look at a couple of patterns of the regular way of expanding these things so you can start to make the link with the next slide. So let's go over binomial expansion of a plus b to the power of 2 and a plus b to the power of 3 before we do anything else. So when you see a plus b to the power of 2, I'm hoping at this point that you're not thinking that you can bring the 2 into the bracket anymore. Some of you were making that mistake earlier on in the year, and it's an easy mistake to make. This has to be written as a plus b times a plus b. A power of 2 means there are two of those things multiplying each other. And in this case, we have what's called a FOIL scenario. Now, FOIL is an acronym that is used to help students remember every multiplication that's involved. The problem with FOIL is when we start expanding a power of 3, it's not going to come into play. We won't be able to use it. So I would rather you think of this as the A multiplies both of the things in the second bracket, and the b multiplies both of the things in the second bracket. So let's expand this. A times a is going to be a squared. A times b and b times a are the exact same term twice. So there's going to be two ab's, and then b times b is b squared. Stuff you've been doing for quite a while. I am going to put the coefficient of 1 in front of both the a squared term and the b squared term, and you're going to see why later. Okay? Now let's do a plus b to the power of 3. Well, with a plus b to the power of 3, that basically means we're doing a plus b as a bracket times what we just did here. We already multiplied two of the brackets together. We're going to multiply a third bracket times that one. So just to save us some time, let's just rewrite the quadratic from the previous answer. And this is what I meant by FOIL doesn't work here anymore, because you don't have just 4 things multiplying. You have 2 things in this bracket and 3 things in this bracket. So this a has to multiply to all 3 of these, and this b has to multiply to all 3 of these. And that's why I kind of prefer the idea of multiple distributivity, because multiple distributivity works for any case. FOIL only works for a binom times a binom. So let's write out all the terms. We've got a times a squared, which is a cubed, a times 2ab, which is 2a squared b, a times b squared, which is just ab squared, b times a squared. Now I like to write these in alphabetical order, so a squared b, b times 2ab, which is 2ab squared, and b times b squared, which is b cubed. So let's group up all of the like terms. So I like to highlight my like terms with little symbols like squiggly lines and stuff. So we've got a 2a squared b there, an a squared b there. We've got an ab squared here and a 2ab squared here. So we're going to get a cubed plus 2a squared b plus a squared b is plus 3a squared b. ab squared plus 2ab squared is plus 3ab squared. And plus b cubed is the last term that doesn't have anybody to join with. And like in the previous example, I'm just going to put the coefficient of 1 here and the coefficient of 1 there. Okay? So we've just expanded a plus b squared, and we've expanded a plus b cubed. And we could do a plus b to the 4, or a plus b to the 5. But with these two examples, that should be enough to introduce the concept of what is Pascal's triangle and what is it useful for. So I'm going to switch slides here. Let me just put down a window pane here. So what is Pascal's triangle? Well, Pascal's triangle is a pattern that's been developed over many, many years. And basically it works like this. So I'm just going to show you how to draw out the triangle. So we're actually going to draw like a pyramid of numbers here, okay? And then we're going to talk about why is this helpful. So Pascal's triangle is organized like this. We start with a 1 at the top of the pyramid, and then you add numbers that are next door to each other. Well, the 1 doesn't have a number next door to each other, so it's a 0 next door. So 1 plus 0 is 1, and you write it in a diagonal direction, like this. Let's do the same thing on the other side. 1 plus 0 is 1. Now for the next row, we're going to do 1 plus 0 is 1. But then these two numbers are side by side each other. 1 plus 1 is 2. And then we do 1 plus 0 is 1. And then you keep going. 1 plus 0 is 1. 1 plus 2 is 3. And this is where I made my mistake in the previous lesson. I thought this was 4 for some reason. 1 plus 2 is 3. 2 plus 1 is 3. And then 1 plus 0 is 1. Okay? Now I want you to look at this row and this row and compare it to the previous slide's coefficients for this guy and this guy. The coefficients for an a plus b squared is 1, 2, 1. Okay? Well, that's the exact same numbers that we got. Oops, sorry about that. The exact same numbers we got here, 1, 2, 1. If you look at the next one, we got 1, 3, 3, 1 as the coefficients for each one of those. Went too far back. 1, 3, 3, 1. So these numbers in Pascal's triangle give us the coefficients of our binomial squared and of our binomial squared and our binomial cubed. So, and that's exactly what this does. If we continued on, 1 plus 1 is 0, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1 plus 0 is 1, that would give us the coefficients of all of the terms in a power of 4. So this is a power of 2. Actually, let me write it this way. So a binomial squared. This is a power of 3. So a binomial cubed. This would be a power of 4. Now here's an interesting question. This would be a power of 1. Does that one work? Well, what is a plus b to the power of 1? Isn't that just a plus b? And what are the coefficients in front of a and b? They are both 1s, which is what that row is telling us. What about this guy? What power would that one be? Well, following the pattern, this would be a power of 0. Does that one work? What is a plus b to the 0? Well, anything to the 0 is 1, and that's the answer you would get at the top of the pyramid. So Pascal's triangle is a really quick way, quicker than actually expanding a power of 4 binomial, to find all of the coefficients that would go in front of the terms for the answer to that binomial to the power of 4. But then you're going to say, sir, how does that help us? We still have to find out what all the different terms are. Well, I'm going to rewrite this last one in a slightly different way. Each term can be thought of as having a and b written in the term. Okay? Now, I want you to look at this power here next to this b would be a power of 1 because it's a b all by itself, so that's a power of 1. Take a look at what the two powers add up to. Now, we called this the degree of a function, and we called it the degree of a term a long time. Now we're going to call it the degree of a term, okay? Now, I don't like this. This is one of those weird things in math that kind of breaks the rules. You're not supposed to add an a to the 2's power with a b to the 1's power because they're not the same base. But that's not what we're looking at here. We're looking at the multiplicative ability of the entire term. I don't know if that makes any sense. They call that the degree. So the overall degree is the addition of those two things because there's two things multiplying with a squared and there's one thing multiplying with b. So there's three things multiplying is basically what that's saying. Well, the powers therefore add to 3. Well, what do these two powers add to? They also add to 3. So following that pattern, what would be the power that would have to be next to the b here so that it would follow the same pattern as those two powers? 3 plus 0 gives me a multiplicative power of 3 for that term. Same thing for the last one. What would be the power for the a that would make that work? Well, that would also be a 0. And that matches the power of our original exponent. So I'm here to tell you that that actually works. If you know what the original power is, you know that you're going to start with the same power and 0, and then you're going to go down 1 power. So the 3 went to a 2 for the a. You're going to go up 1 power for the other term. 0 went to 1. So this might make a little bit more sense if you actually see another example. So let's do a plus b to the 4. And then we're going to do x plus 4 to the 3. Okay? Let's do a plus b to the 4. So the first thing you would do is you would write Pascal's triangle all the way up to the fifth row, which is the 4th power. Okay? So let me be clear on that. You're starting by counting at 0. So 0, 1, 2, 3, 4. That's the 5th row, but it's the 4th power. Okay? You would find all your coefficients. So we're going to write all of our coefficients. 1, 4, 6, 4, and 1. Then you're, and I'm just going to move this down here, folks, so it's not in our way. That didn't work. Let's try that again. Okay. So, like I said, I wrote the coefficients down. Now I'm going to write AB for each one of them. AB. They're all added together. AB. 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 And AB. And then what I'm going to do is I'm going to cycle through all of the additions of powers that add up to 4. So the first one's going to be 4 and 0. Then I'm going to drop 1 for the A, so that's going to become 3, and I'm going to add 1 for the B. Those two add up to 4. These two are going to be the same, 2 and 2. I'm going to drop 1 from the 3, it becomes a 2. Add 1 from the B, it becomes a 2. Okay. I'm going to drop 1 from the A, add 1 to the B. Drop 1 from the A, add 1 to the B. And you've now expanded that binom to the power of 4. And you didn't have to do a plus b times a plus b times a plus b times a plus b. Pascal's triangle gives you all the coefficients, and then you just cycle through all of the powers that add up to 4, starting with a power of 4 on the first term and a power of 0 on the second term. We're going to clean this up. Anything to a power of 0 is just 1. And we usually don't write the coefficient of 1 if it's a 1 in front. So we're going to have a to the 4 plus 4a to the 3b1. We don't write the power of 1. Plus 6a squared b squared. Plus 4 a to the 1, a to the 1 b to the 3. And then this will be 1 times 1 b to the 4. The a0 is a 1, so all we have is a b to the 4. And that is your final answer. That is a wonderful thing when you have to do expansions of binomes to higher powers than powers of 2. And I know for myself, when I'm doing a binom squared, I don't actually do a plus b times a plus b. I use 1, 2, 1. I remember that row from Pascal's triangle. 1, 2, 1. Sorry. And I just cycle through those two powers for the terms in all three of the terms. And it's much faster, in my opinion, than even foiling. But it has to be a binom squared, right? So it can't be used for like x plus 5 times x plus 7. That has to be FOIL. But if you had x plus 5 squared, you could use it. So how can this get a little bit more complicated? Well, let's look at this example next. This is a more like a polynomial because you've got an x and a 4 instead of an a and a b. Okay, we're going to do the power of 3 version. So let's look at the power of 3 row. The power of 3 row is 1, 1, 3, 3, 1. Okay. So 1, 3, 3, 1. Then we're going to cycle through our powers, but we have an x, and I'm going to write it in this order, folks, because I want it to follow the order of a and b. We'll change the number and letter order in the final version, okay? So, so I'm going to put x first and then 4. So what's the power that goes with x? Well, the first power is always going to match the power of your bracket, and then the second power is going to make sure that those two add up to 3, which is the degree of that power. Then we're going to do an x2 and a 4 to the 1. We're going to do an x1, 4 to the 2, and then an x0, 4 to the 3. So what's going to happen here is some of the numbers are going to combine with the coefficient. Okay, so that 4 to the 1 and that 3 are actually going to combine together. So it's going to look a little bit different than the ones we did before, but it's not any more difficult. So what's the simplification of 1x to the 3 times 4 to the 0? Well, 4 to the 0 is just 1, and it's 1 times x to the 3, so that's just x to the 3. 4 times 3, and I hope everybody sees it's 4. 4 to the 1 is just 4, and that's going to multiply the 3. Okay, so 4 times 3 is 12, x to the 2. 4 squared is 16. 16 times 3 is 30 plus 18, which is 48. X to the 1. And then 4 to the 3, I forgot my bracket here. 4 to the 3 is 64. 64 times 1 times 1, because x to the 0 is just 1. And that just gives 64. Much faster than doing x plus 4 times x plus 4 times x plus 4 and actually expanding everything. Now, it does require you to have Pascal's triangle handy, though. Okay, and depending on how high that power is, that can take a little bit of time. But once it's done, you can always refer to it. So just to show you a little bit of, and I hope I can do this here, a little bit of history. If you look up Pascal's triangle, and I actually just went to Wikipedia. Now, I know Wikipedia is not considered to be a fantastic site to be citing, but it's getting better because people can go in there and actually say, no, this is not true and change it. So I'm going to use Wikipedia, and I'm sure you could find it on other sites as well. And I just typed in Pascal's triangle Wikipedia. So they have a little animation here of Pascal's triangle filling up, just like I showed you. You're just adding down, right? And if you had to go one more row, you would do 1 plus 4 would be 5, 4 plus 6 would be 10, 6 plus 4 would be 10, 4 plus 1 equals 5. So you'd have the ones on either side of that as well. Well, what's interesting about this website is the history. So when I read this, I actually didn't know this. I thought Pascal was the person who developed this triangle. This triangle has been known since before the 2nd century BC. A gentleman by the name of Pingala. And they show you the images that were used, okay? And I believe there's some Chinese mathematicians as well that was working on or were working on this triangle. And there are usefulnesses beyond what I'm showing you here. They have to do with probability, which has actually been always one of my kryptonites. I struggle with probability. It's something my brain has always had trouble doing. But these numbers do follow some sort of I can't say the word, combinations in probability, okay? So permutations and is it combinations or anyway, I'm forgetting this. Yeah, permutations and whatever that other word is. Thank you. Yeah, so there's a lot of patterns inside of Pascal's triangle that he himself figured out, I think, beyond what some of the historical mathematicians figured out. Down here, they actually have the generalized equation of Pascal's triangle. Sorry, of binomial expansion, my mistake, using Pascal's triangle. So if you have x plus y to the n, meaning any power, it would be a0 x to the n, where a0 would be the first number from that row of Pascal's triangle. X to the n would be the same power that's there. And then if you look at what happens to the next x, it goes to n minus 1. And then all of a sudden the y shows up with a power of 1. And then the x goes to n minus 2, and then the power goes to y to the 2, plus dot, 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 and you continue all the way up to a to the n, y to the n. So this is the general equation of the binomial expansion. Combinations. That's the word. Thank you. Combinations. So, going back to my smartboard here, you now have been introduced to Pascal's triangle and its power. What kind of questions could I ask you to do? Well, I could ask you to do this one. What would 2x plus 4y to the power 4 be? So if you go to your row for power 4, it's 14641. So we would write 1, 4, 6, 4, 1. Now in this case you have slightly more complicated terms inside your binom, but you would just write 2x, that's a bracket there, sorry, 2x to the power 4, 4y to the 0. Now, when you write 4y to the 0, eventually you're not going to write that at all because anything to the 0 just becomes 1, right? And then you do 2x to the power of 3, 4y to the 1, and then 2x to the power of 2, 4y to the 2, 2x to the power of 1, 4y to the 3, and the last one would be 2x to the 0, which again you don't have to write anymore because anything to the 0 is 1, and 4y to the 3. And then you would simplify. Now, we're going to be reviewing the exponent rule soon, but this is grade 9. You've got here the situation of a power. So that power 4 does affect both the 2 and the x because both of those are multiplying here, but you cannot bring the 4 into this bracket up here with the plus because of the plus, okay? So this is something that a lot of students mess up. You cannot bring a 4 into a bracket that has a plus or a minus. Sorry, you cannot bring a power, I should say, into a bracket that has a plus or a minus in it. But you can bring it into a bracket that has a division or a multiplication in it. So it would be 2 to the power 4, x to the power 4, simplify that. And then 4 times the 2 to the power of 3 would be 8. 4 to the power 1 would be 4, sorry. So 4 times 8 times 4 would all join together, okay? So you should be able to do that. I'm not going to do it here, okay? That is not hard to do. The hardest part is remembering Pascal's triangle gives you the coefficients, and then the how the powers all just like kind of, you know, go from a higher number and then drop by 1, drop by 1, drop by 1, start from a 0 and go up by 1, go up by 1, go up by 1. Okay? Here's another type of question that I could ask. What is the fourth term in x plus 5 to the 10? Now, to be able to do that, you would have to do, and follow me here, 11 rows of Pascal's triangle. Okay? You're going to have to do it in the homework tonight. But let's just pretend that we knew the coefficient. Everybody should be able to tell me, if you think about it, maybe you can hold off on the chat answers here for a second. Okay, let everybody have a chance to think about it. What would be the power to the x and what would be the power to the 5 for the fourth term in this expansion? So I want you to think about this. You start with x and 5. What are the first powers? The first powers are 10 and 0. Well, go 4 terms in. So now maybe chat can answer. What would be the power to the x? What would be the power to the 5? And start with the x one alone, please. Just tell me what the power to the x one would be. That is correct. So don't give me the 5 one yet, because I want to talk about that. If you know this one, oh, somebody said 6. Let's do it together, okay? You're starting with 10. The next one would be 9, and then it would be 5 to the something. Okay. The next one would be 8 and 5 to the something. And then the next one would be 7. So I know why you said 6. It's a very easy thing to get as a mistake, okay? You've got to think of this as how many, because you're counting the 10 as the first one, you're not starting at, I don't know how to explain this. You're not subtracting 10 minus 4 to get 6. That's not how it works, okay? So you have to count from 10. 10 is 1, 9 is 2, 8 is 3, 7 is 4. Okay, so the fourth term in is power of 7. So you got to be very careful with that, because I was expecting somebody to say 6. But as soon as you know that first one, you immediately know the second one. You don't even have to think about it anymore, because what do both of those powers have to add up to? As I said before, they have to add up to the power that was given to you in the original degree. Okay, so 7 and 3 are going to add up to 10, so I know that the second one has to be power of 3, which somebody had already answered. Okay, so just be very careful about that 10 minus 4 thing. It does not work that way here. You've got to technically count them, or you can do 10 minus 4 plus 1. Because the 10 counts as your first one. All right? When you do 10 minus 4, maybe this will help you understand. When you do 10 minus 4, you're counting how many steps you've jumped down to get to 6. Okay? And that's technically not what we're doing here, because this one is the first one. So I don't know if that helps or not, but it's a little bit different. And that is today's lesson, folks. I am going to give you some homework on a handout. And I believe the answers for all of the questions except for the first one, because the first one's going to be make Pascal's triangle up to row 10. Sorry, row 11, which is the 10th power. So I'll be posting that on the Google Classroom soon. Are there any questions? That was one of the easiest lessons. I like the tattoo comment. That's awesome. I don't know if that's necessary, but you'll start to see some patterns. And I'm actually gonna. I forgot to do it for the first class, but I'm gonna post a YouTube video from Numberphile on Pascal's triangle. It is amazing the different patterns in that Pascal's triangle. Like, it is mind blowing. So if you have some extra time, watch that video. But do the assignment first. Are there any questions before we move on to stopping the stream? Okay, so if there are, your assignment tonight will probably let you know if you need any extra help. As always, just email me. Just to mention something here, folks, I didn't know where to put this lesson because it doesn't necessarily fit perfectly. Here, let me just switch. So you can see me here. It doesn't fit perfectly in some of the other concepts we've been learning. It's a little bit of polynomials, and it's also a little bit of your ISU. It's somewhere in there, okay? So I decided to show it because it is, I believe, brand new for some of you. I know some of you already know it, but I think it's brand new for some of you. It is extremely useful, and we're going to be using it because when we get into rationals, we are going to be expanding some binomes squared sometimes. This is pretty much all we're going to be doing for binomial theorem for this course, except when we need it to expand certain things in the rationals section. So when we get into rationals, we might have binomes cubed that we're going to have to expand as fast as possible, and that's where this is going to come back into play. So we're not really doing anything more about that this year. That's all I need to do for the curriculum. We can't do too much, then the teachers in the future have nothing to show you. But anyway, so I'm gonna stop recording. Sorry. So I'm gonna say bye to everybody for the recording.